This MCQ is from NEST 2019, shift 1, question number 11. The speed, frequency of revolution and the radius of the electron in the nth orbital in the Bohr model z equal to 1 are denoted by Vn, f rev n and Rn respectively. Let f of n be the frequency of the photon when the electron makes a transition from the nth orbital to n-1th orbital. Then f rev n is directly proportional to 1 upon n squared. Vn is proportional to 1 upon n. Rn is proportional to n squared. For large n much greater than 1, fn equals f rev n. Okay? Okay. So we are given the speed, frequency of revolution and the radius of revolution in the nth orbital. Bohr model z is 1, Vn, f rev n and Rn. Okay? Now if we know these two formulae, which we have been using from quite some time now in almost every MCQ, we are either using Rn, Vn or En. Okay? Rn varies directly with n squared, so option C is correct. Okay? Vn varies inversely with n, so option B is also correct. Okay, option B is also correct. So these are two very basic formulae. Okay, now let us come to option A, because it deals with the frequency of revolution. Okay, it deals with the frequency of revolution. Now we can say that V is equal to R omega. Correct? V is equal to R omega. Right? Assuming that the electron that performs uniform circular motion, that's what we do assume in Bohr model. Okay, V is equal to R omega. And if we want the frequency of revolution, okay, we must write omega as 2 pi f. Right, we must write it as 2 pi f. So what can I say about f? F is equal to V upon 2 pi r. Right, V is equal to, sorry, F is equal to V upon 2 pi r. So F is directly proportional to Vn upon R. Okay, F is directly proportional to Vn upon R. Okay, therefore F will be proportional to what? Vn is directly proportional to 1 upon n, and if Rn is proportional to n squared, 1 upon Rn will be proportional to 1 upon n squared. Okay, therefore f rev n, frequency of revolution, is directly proportional to 1 upon n cubed. Is it right? No, option A is not right. Okay, option A is not right, because in option A they say it should be proportional to 1 upon n squared, but we have got cubed. Okay, so it is not A. B, C were very straightforward, but now let's go to D. Okay, now let us go to D and see if we indeed get it. Okay, for large n, Fn is equal to f rev n. Okay, alright, now I think what we should do is, to get it right, we need to first find out what is f rev n. Okay, let's find it out. F rev n, which is V upon 2 pi r, so Vn upon 2 pi Rn. Okay, 1 upon 2 pi into Vn e squared. Now I'm not writing z because they have given us that z is 1. Okay, z is 1, so I'm not going to write that, into e squared upon 2 epsilon naught nh into, now we need to write the reciprocal of Rn, so pi e squared into me upon epsilon naught into n squared into h squared. And as expected, n and n squared will give us n cubed. Okay, fine. Now let us go for f of n. Now what is f of n? It is the frequency of the photon which the electron, when the electron makes transition from nth orbital to n minus 1th orbital. Okay, now pay attention. Suppose this is En and suppose this is En minus 1. Okay, the electron is going to make a transition like this, and thereby it is going to emit a photon of frequency h nu. Okay, now they are saying let f of n be the frequency. So according to them, this will be h into f of n. Now we have to use the formula which Balmer gave us empirically, and which was later provided a proof. Okay, theoretical proof from Niels Bohr. Okay, and if you remember that formula is 1 upon lambda. Okay, 1 upon lambda is equal to Rydberg's constant r. Okay, Rydberg's constant r into 1 upon n squared minus 1 upon m squared. I hope you remember this. So it will be 1 upon n minus 1 squared minus 1 upon n squared. Do you remember this? Yes, okay. Now 1 upon lambda is what? Look, lambda nu is equal to c. Okay, so 1 upon lambda will be nu by c. Okay, 1 upon lambda will be nu by c, or well, now nu is f of n, so I can say f of n is equal to rc into this. Okay, now let us take the LCM. So it will be n squared minus n minus 1 squared, so n squared minus 2n plus 1 upon n squared into n minus 1 squared. Okay, alright. Now what is RC? R is this. Okay, R is this, Rydberg's constant. Unfortunately I had to learn that formula by heart, no other choice. So C goes, so let me cancel it right here. Okay, into n squared minus n squared, so that's 2n minus 1 upon n squared into n minus 1 squared. Okay, okay. Now look, they want us to go for the f of n value when n is much greater than 1. Okay, now this is suddenly a limit problem. Now. Okay, so limit as n tends to infinity 2n minus 1 upon n squared into n minus 1 squared. Okay, now what I can do is, well, not exactly I am required to find the limit, but I can say that this will be equivalent to, okay, this will be equivalent to limit as n tends to infinity 2 divided by n cubed. Okay, or well, better I should have put it like this. This will get closer and closer to this. Okay, because see, look, the numerator is of the order 1, it's n, and the denominator is of the order of 4, right? It is of the order of 4, which means if we continue to put larger and larger values of n, okay, the denominator will obviously dominate the numerator, and effectively it will be 2 upon n cube. Is it clear? Okay, therefore for large n, well, see, now why did I not make use of the limits? Because for limits, if I make use of limit, then I need to go for 0, but I don't want that. Okay, limit is 0, we know that, but that's not something that we want. Okay, that's not something that we want, because we want to compare the expressions if we have a very large value of n. Okay, so for large n, what can we say about f of n? F of n is equal to RC into 2 by n cubed, or it will be m into e raised to 4 upon 4 into epsilon naught squared into h cubed into n cubed. Okay, and what is the expression that we had obtained here? F rev n. Let's now go term by term and see if we indeed get that. Okay. Okay, now look, this is 4, 2 into 2, 4. Okay, then we already know that it is n cubed. We had already encircled it. Sorry, n cubed. Yes. Now let's go for mass of electron into e raised to 4. Mass of electron into e raised to 4. Okay, so the entire numerator has now been taken care of except for that pi, but that pi is getting cancelled here. Okay, that pi is getting cancelled. Now, are there 2 powers of epsilon naught in the denominator? Yes. Okay, 2 powers of that. And do we have h cube? Yes, we do have h cube there. H into h squared, and that is h cube. Okay, so what does it mean? What does this result tell you? This result tells you that if the electron is making a transition from nth stable state to n minus 1th stable state, provided both n and n minus 1 obviously are very large, then the frequency of revolution of the electron will roughly be equal to the frequency of the photon that it emits. Okay, the frequency of the photon that it emits. So option D is correct. Now look, although option A did not turn out to be right, it actually formed the basis of the solution for option D. Okay, because see, if we are saying that f of n is equal to f rev n, we have to compare both the expressions. And how did we find f rev n? We found it out by using the formulae for Vn and R. Got it? And we also had to know the formula for Rydberg's constant in order to find the expression for f of n, and then we suddenly switched to limits. We argued that both these expressions, or both these functions rather, are asymptotically similar. Okay, now let's check that. Let us check that. First of all, let us go for 2x minus 1 upon x squared into x minus 1 the whole squared x greater than 0. Okay, that's the value. And now let us go for 2 upon x cubed. Okay, now see, look how quickly both the curves merge, right? So if I go for n equal to, let us say 10, let's go for n equal to 10 and let's just try to find out the difference between them. Okay, let's try to find out the difference between them. So it is 0.002346. Okay, and how about the bottom one? 0.002. So that difference is pretty small, right? That difference is pretty small.